Assalamualaikum and a very good day to all. I'm Muhammad Farhan bin Faizal Zainif and I will start with the introduction of the experiment. So for this experiment, we are investigating the residence time distribution in a tubular packed bed reactor. What is residence time distribution? Residence time distribution, or RTD, of a chemical reactor is a probability distribution function that describes the amount of time a fluid element could spend inside the reactor. It also shows the characteristic of mixing that occurs inside the reactor. It can be determined experimentally by injecting a chemical that is inert, such as sodium chloride, that is called a tracer. It is essential in determining the operational cost, reactor volume, and flow rate of the reactor. It is one of the key elements in developing a dynamic model for the reactor design and operation. In chemical processing, a packed bed reactor is a hollow tube or pipe that is filled with the packing material. The packing material can be randomly filled, such as research rings or a specifically designed structured packing. Packed beds may also contain catalysts such as zeolites or activated carbon. The purpose of a packed bed reactor is to improve the contact between two phases in a chemical process. Packed beds can be a chemical reactor, can be used in the distillation process, and also acts as a scrubber. Okay, so for our experiment, we have two objectives, which is to investigate the effect of step change in countercurrent or co-current mode, and also experiment B, which is to investigate the effect of pulse input on countercurrent and co-current mode. And that's all from me. Thank you.
Okay, hello, hi, my name is Fatih Anur binti Muhammad. So today I'm going to explain the methodology part for our experiment A, which is the effect of step change input, but just for the counter current mode. Okay, first of all, we have to perform the general start procedure and then set the valve appropriately for counter current mode, which is for the V3, V5 and V10, we have to remain closed. And then open valve 1 and pump 1 and let it flow for the flow rate is for 500 milliliter per minute, and just let it flow and wait for the data until it will be at the constant steady state. And then for the second part is for the effect of pulse change input, which is the first main difference is we have to open the pump 1 and let it for 3 minutes, and then after the 3 minutes reading, we open the pump 2 for 2 minutes and then continue back to close the pump 2 and back to pump 1 until the reading back to the normal again. Hi, so sorry for the interruption. Now let us continue with the part for the co-current mode. Okay guys, so for the co-current mode, for the effect of step change input, first you have to perform the general startup and you have to make sure that valve 2, valve 4 and valve 9 remain closed while the valve 3 and 5 were open. And then you have to adjust the V1 until it obtains 500 milliliter per minute of the flow rate, and pump 1 was switched on. While V6 are open and also valve 8 to obtain a gas flow rate of 1.0 liter per minute, and you have to observe the conductivity reading of CT2 and let it stabilize for a while. And then after that, you have to switch on pump 2, and V15 was closed and valve 10 was open, and just have to record the reading of CT2 at 1 minute interval. Okay, so for the effect of pulse input, the step
were the same until the step 5, which is the conductivity of reading of CT2 was observed. And then the pump 2 will be switched on and let it dosing for 2 minutes. After 2 minutes, you have to switch off the pump 2. So you just continue the recording until the conductivity of reading was constant. So that's all for the methodology. Have fun with the experiment.
Hello, my name is Harshan Madushan, and today I'll be discussing about results and discussion. Hello, today I'll be explaining about the results and discussion. So for experiment A, we will be observing the effect of step change input in counter current flow. The liquid flow rate I'll be using is 0.05 LPM and the air flow rate will be 1.0 LPM. So as you can see, this is the graph of concentration against time for step change of counter current flow. Next, for this, it's the graph of ET against time for step change of counter current flow. So now I'll be explaining about the effect of step change input in co-current mode. So the liquid flow rate will still be the same, 0.05 LPM, and the air flow rate also will be kept constant, which is 1.0 LPM. So over here you can see the graph of concentration against time for change in co-current flow. So next, this is the graph of ET against time for step change in co-current flow. Now we shall proceed with experiment B. In experiment B, we will study the effect of pulse input in co-current and counter-current mode. So first of all, we will see the effect of pulse input in counter-current mode. The liquid flow rate and the air flow rate are kept constant, which is 0.05 LPM and 1.0 LPM respectively. For this, as you can see, this is the concentration graph of concentration against time for pulse input in counter current flow. Next, you can see the graph of ET against time for pulse change of counter current flow. Now we shall observe the effect of pulse input in co-current mode. As usual, liquid flow rate and air flow rate are kept constant at 0.05 LPM and 1.0 LPM respectively. This is the graph of concentration against time for pulse input for co-current flow. Next, we can see this is the graph of ET against time for pulse change for co-current flow. So over here you can see the table for our experiment. The parameters are mean residence time, variance, skewers, and dispersion dimensionless. So we calculate the parameters for both objective, step change input and pulse input for both flows, counter current and co-current flow. For the discussion part, I'll first explain what is step change. When step change is introduced into our feed, the amount of tracer will be continuously fed into our reactor. Thus, in the end, we'll receive a constant amount of concentration of our tracer in our reactor. That is step change. So now I'll be entering the discussion part. So I'll first explain to you about our step change graphs. So as you can see, what you can see from the graph before, the concentration graph for co-current mode, it requires 12 minutes before it actually reaches a steady state value. But for counter current mode, only 11 minutes, then it will reach a steady state value. So from here, we can derive that for counter current mode, it's much faster, the residence time is much lower than co-current mode. So for the step change, for counter current flow, the residence time for counter current flow is much lower than the residence time for co-current flow. For counter current flow, as you can see from the previous table, it's 10.6, but for co-current flow, it's 20.28. So what can we derive from this information? From this information, we get to know that counter current flow is more efficient compared to co-current flow because it needs less time to produce our product. Not only that, as you can see from our previous tables, other parameters are also lower than co-current mode. So now we shall move on to our second objective, which is our pulse input. What is pulse input? Just now I have explained to you about step change. Step change is when the tracer is continuously fed into our reactor. Pulse input is when our tracer is only fed at a certain period of time to see the change in the concentration. So now for our pulse input graph. Just now when I explained the results, you have observed that the pulse input graph is a bit different from the step change graph. So for pulse input, what we can see that at the 6th minute, it start increasing. There's a sudden increment of gradient till it reaches its peak at the 8th minute. Then there's a sudden drop. Why is this? Because at the 6th minute, we injected sodium chloride into our reactor. That's for counter current mode. Now for co-current mode, you can see that it started to increase at the 5th minute, but then when it decreases, it takes a longer time to reach the steady state value. So as you can see from the table that I showed in our previous slides, the table, as you can see, when you compare co-current and counter current, the parameter, especially for residence time, the residence time for co-current is longer than the counter current. And for other parameters like skewers and dispersion dimensioners, counter current mode also shows a lower value when compared to co-current mode. So even for pulse input, counter current mode or counter current flow is more efficient compared to co-current. This is why in industries we use more counter current flow instead of co-current. That's all from me. Thank you.
Hi everyone, my name is Guru Shafika and I will explain about the error and modification in this experiment. Okay, in this experiment, we have 4 errors. The first error is fluctuation in the reading of the reactor. This error can be avoided by repeat the experiment a few times and calculate the average reading of the conductivity. For the second error, it is the adjustment of the valve positioning. This error can be overcome by carefully position the valve so that we can get the valve that we want without error. Okay, for the third error, the trapped bubbles inside the reactor. We can overcome the error by washing the reactor and remove the bubbles inside the reactor. And for the last error, it is the inconsistency of the water and air flowing inside the reactor. This error can be avoided by constantly observe the flow and the reading of the reactor so that we can maintain the consistency of the desired value. So the conclusion is basically we have to minimize our error so that we can get the desired desired output. So that's all from me. Thank you.
Hi, I'm Dr. Shalini. I will conclude our experiment. Okay, for the experiment A, the effect of step change input. Okay, for the mean residence time, we found that in a tubular reactor for the counter flow have a mean residence time faster than the co-current flow. And then the time taken for the concentration to reach its steady state in counter current is faster than the co-current. Okay, for the experiment B, the effect of the fast input, we found that both co-current and counter current reach a maximum concentration at a certain time when the tracer, which is a sodium chloride, is injected to the reactor. The mean residence time in a tubular reactor for the counter current is faster than the co-current, and the time taken for the concentration to reach its steady state for the counter current is faster than the co-current. As the variance and skewness that has been calculated, we found that the counter current is the best choice to operate the system compared to the co-current for the both experiment. Okay, thank you.